including also energy. And I'm delighted to give a talk on subsurface energy storage. Particularly, I'm going to focus on hydrogen today for a reason that you will get to know in a moment. The talk I'm going to give and also the lecture, which would hopefully engage you as well, is given by me, but many students and colleagues have contributed in the story that I'm going to take you through. So let's start the lecture, and I hope that you could also engage or ask your questions through the chat box that you have. Okay. Whenever we produce something to be either distributed or it should not be distributed, there must be a storage in between. For almost everything in our daily life, resources that we have or other things, whenever we produce it and it has to be distributed, there must be a plan for storage in between. Otherwise, the reliability and fidelity of the system would be under question. And that matters for everything almost in life, including also topics related to energy. And not only energy, but also climate actions would require a lot of these sort of storage platforms to be developed. I will speak about energy in a moment in greater detail, but for climate, we produce a lot of CO2 and other greenhouse gases that we shouldn't. So we need to really store them and trap them and keep them safe for a long period of time because they shouldn't be in our atmosphere. So that's also climate driven as well, that where you need actually storage. More importantly, also for water resource management, we need to also think of storage platforms. We are creating artificial islands and we dry lands to make them habitable because the population of the earth is increasing every day. And there we need to arrange and manage how are we going to supply confidently fresh water or natural water resources as well. There are places where, or seasons in which we have less precipitations, so low resources of natural water resources. And then there are seasons which we need water for agricultural activities or just city life. And there we need to really get the water properly and manage it. So the storage and proper storage management is also crucial in water resource management too. Today, I'm going to focus about energy, but that storage platform is not really limited to only energy. It does matter to many other aspects, especially climate and water resources. With energy, when it comes to energy, we know that the future we expect to have a large contribution, significant contribution of renewable energy for our society. But these energy resources are intermittent by nature, which means there are seasons with high wind, we can produce a lot of wind power. There are seasons with a lot of sunshine, we can get a lot of solar energy. But there are also moments, nights or no wind seasons, where we don't really produce much. And so we have to have a right plan for a storage of energy if we want to really rely on them to supply the energy of the future green world. So let me take you to this story of storage for renewable energy in the scale that I call it large scale. So I have written here, large scale energy storage is crucial. And let me tell you, what does that large scale mean? How much energy do you think we consume in different countries? I have a poll here, and I'm asking everybody in the audience, please do contribute in these questions. I'm not sure if I have the chance to see any texts in the Zoom. I'll try to see if I can see the chat box or something, but there is a poll here, and you should have already seen the poll. It's I have lost my mouse a bit, but I'll be back. So I'd like you, please get engaged with the poll. I see numbers are coming. how much energy do you think in the country, the Netherlands, we consume per year? 800 kilowatt hour, 800 megawatt hour, 800 gigawatt hour, or 800 terawatt hours. So I see numbers coming through, which is great. And this is approximate, of course. So if it's 800 or 790 or 850, this is the scale which matters to me, because I want to define what do I mean by large scale. Okay, so you should have already 1 minute of the poll. So the right answer is actually the item D. In the country Netherlands, we consume about 800 terawatt hours of energy. Tera means 10 to the power 12. So those who answered D got it right, and others didn't get the right scale. So Netherlands has about 17.5 million residents. And so item D is the terawatt hour scale in which the country consumes. Now, if we go to, I need to somehow get rid of the poll. Can we close the poll, please?
I just closed the poll.
Yeah, okay.
For you well.
Okay, I cannot do anything with my screen any longer.
Polling is closed, and I just shared the results.
Okay, let me
just stop share results. Now it should be
excellent. Excellent. Yeah. Thank you. Okay, so back to the questions. Now the second quiz is about, so Netherlands was 800 terawatt hour. How about USA? How much energy do you think in America people consume in 1 year? And these are rough estimates. So for Netherlands, it was 800 terawatt hour. And now USA, about 300 million residents. How much energy do you think in the USA we consume in 1 year? So thanks to those who already have submitted their answers. So I have A, B, C, D, 4 choices. 800 terawatt hour, the same as in the Netherlands. 1,000 terawatt hour, 10,000 terawatt hour, 30,000 terawatt hours. So these are really big numbers, by the way. So 10,000 terawatt hour is a lot of energy. Okay, so it's 50 seconds past the poll. So in 8 seconds, 7, 6, we are going to close it. Thanks a lot to many of you. Actually, plenty of you participated. The right answer is actually item D. And the majority of the people who actually participated in the poll got it right. So in the US, about 30,000 terawatt hour of energy is being consumed in 1 year. Now I move on to China. What do you think? Now it's a 30 seconds now, because now you get the scales right. I need to know what do you think about China? So you have 30 seconds to reply. US was 30,000, and I'm asking what China is consuming. Okay, so we have 30 seconds. So the poll is closed. Thanks a lot. The majority did right. So China is consuming 37,000. So 7,000 more than US. And that 7,000, to give you a scale, is almost 10 times of the entire energy consumption of the Netherlands. So it's 37,000 is a lot of energy. And this is why this is the point that I have today to make, is that we get a kind of a feeling about what do we mean by energy transition and moving the grid from a fossil-based energy supply to renewable energy supply, there is much to be done. Now, you will get better feeling as I will continue through my slides. Now, well done. Majority of the participants did it right for China. Now, my last question in this slide is about, how about India? And many of you are participating from India. I expect you get it right. Do we have 1,000, 5,000, 11,000, or 20,000 terawatt hours of energy in India? 30 seconds again. Please do supply your responses. I see plenty of responses. Thank you a lot for being very active. Okay, so that's the time is up. Now in India, we have 11,000 terawatt hour energy consumption. And that would mean that these are the results of each country. And you can actually refer to IEA, International Energy Agency.org organization, and look up your country. If you are connecting from Singapore, you just go to your browser, type iea.org/countries/Singapore. And there you will see how much energy are you consuming, how much energy are you importing in your country, and how much energy you are supplying. And there you will also notice one factor there, that the total consumption of energy is written in the unit of megaton of oil equivalent. The equivalent is actually megatons of oil. And there you need to do another conversion from MTOE, megatons oil equivalent, to terawatt hour. There you will get a feeling about how much terawatt hour of energy you're speaking about or you're consuming. For Singapore, if I correctly remember, it's about 400 terawatt hours, but you can go and check. And I'd like to ask you, please go and check and search different countries and see where are we in the entire planet Earth. Now the largest scale, which was a qualitative word, is now being more quantified. By large scale, we mean a lot of terawatt hours of energy. And if we want to store energy, we are not talking about an energy that you would need for a smartphone. We are talking about energy that you would like to store to supply the demand of a country. And that's what we are doing today with fossil fuels. With the gas, oil, coal, whatever resources we have, these are the scale of consumption. And if we stop them today, there is no plan to supply everything from renewables, so they are increasing massively. But at the same time, the storage platforms need to be developed in these scales. Now, giving you this kind of sense about the consumption scale, let me give you also another feeling about how much energy can we store. We have one kind of a storage of energy in the form of electricity. Electricity-based batteries are used everywhere in our daily life, in a normal phone like this, also your laptops, and many places you have electricity-based battery storage. We have different kinds of storage of energy. And so you could have a small batteries like AAA batteries to C-type batteries to smartphones, all the way to a Tesla car battery, an electrical vehicle battery. The AAA battery, to give you a sense, stores about 2 watt-hours, 2 watts, which means for 1 terawatt, you need a lot of them. Tera is 10 to the power 12. So this stores about 2. This stores about 10 to 12 watt hour. The C battery, phones about 12 or so watt hours. I have a question for all. What do you think is the scale, not an approximate range of capacity of an electrical vehicle battery? How much energy do you think the battery of an EV can store? Is it 0.1 kilowatt hour? Is it 10 kilowatt hour, 100, or 1,000? This is a battery which you could have in the Tesla car for a passenger car, would allow you drive about 400 or 500 kilometers or 250 around miles. And you have 30 seconds to supply your response. In 3 seconds, so that's it. So I'm pleased that many of you got it right, but also we have other answers than the right one. So the scale of a storage of a Tesla car battery is around 100 kilowatt hour. 100 kilowatt hour. Now let's do a little bit of mathematics here. How many of Tesla car batteries you would like to have in order to store the energy that you need for Netherlands? You would need 8 billion of these batteries. And there are 8 billion people living on this entire planet. So you would need 8 billion EV batteries to store the energy that you would need to supply the entire year consumption of a country with 17 to 18 million residents. We are not talking about India, China, US, Singapore. These are massive, massive numbers. I'm not going to speak that we don't even have minerals for them. We don't have resources to create and fabricate them, but it's just unfeasible. So how can we store energy such that you can target these massive scale of energy storage? There is when engineers come to play major role to unlock this puzzle. We cannot be obsessed with one way of a storage, and we think that we need to only put all our resources in advancements of one type of energy storage, because that's not wise and not feasible even. The entire world's energy is so massive that we don't have enough materials even to fabricate these many batteries to store the energy that we would like to have. So my question to all is, how else can we store energy if we are targeting the largest scale, which means terawatt hours? If we go now to different sources of energy or forms of energy, we see that there are massive opportunities there that can be exploited for this purpose. The beauty of energy is that it can be converted to different forms. It doesn't have to stay in electricity. It doesn't have to be produced in electricity form. So how else we could transfer or convert energy to? You look at this graph. If you use your energy to compress gas, and when you need energy to let the gas be decompressed and rotate a turbine for you or create work for you, move a piston or do work for you. Yeah? There you can store energy in the form of compressed gas, like air. That is another form of a storage of energy, because you can use energy to compress something for you. And when you need energy to let it decompress and do work for you. You could pump water to uphill. If you are in hilly environment, you can pump water to go uphill, and when you create artificial dams or things like that. And when you need energy, let the water come down and then rotate a turbine for you or do other forms of work for you to create for you either work or energy. You can use your energy and heat up water. And there you can target more storage capacities. This is gigawatt hour scale, not kilowatts. Giga is 10 to power 9. Kilo is 10 to power 3. Especially you could do electrolysis, use energy, solar and wind power. Through electrolysis, you can create hydrogen. There, if you use hydrogen as your energy storage carrier, as energy carrier, in 50 bars, if you compress it in 50 bars, in room temperature, 1 cubic meter of hydrogen can store more than 30% more than a Tesla car battery. 1 cubic meter of hydrogen in 50 bars, still gas, would store more than an EV battery. You can compress it higher more, like in 200 bars, then you will make it a lot more. You can capture CO2 from the atmosphere or exhaust of factories, take CO2, have hydrogen from electrolysis, and do chemistry to create green methane. Green methane would store at the same thermodynamic conditions about 4 times of a Tesla car battery in 1 cubic meters. Obviously, you will have to do the work to create it, but these are the forms of different forms of the way you could look into energy. Here you can target a lot of larger scales compared to electricity-based batteries. But obviously, the discharge time would be affected by the scale that you would target. It would take some weeks to create hydrogen, to bring it to the network and create energy with it. So you need to really plan it ahead of time. Or if you go to even larger scale of methane, for example, in gas fields with green methane, then you need to also appropriately plan your energy consumption, demand, and others, as we are doing today for fossil-based energy production. So here it looks like that we have a solution to target larger scale, but the story is not yet fully complete because we just changed the form of the energy. We haven't yet found a place to store it. What do I mean by this? Imagine you convert your energy to hydrogen. How much hydrogen do you need to store 1 terawatt of energy? 1 terawatt is 10 to power 12. How much hydrogen you would need at 50 bars and 25 degrees centigrade to store 1 terawatt? Tera is 10 to power 12. Tesla car battery was 100 kilowatt, meaning 10 to power 3 times 100 means 10 to power 5. We are targeting 10 to power 12 now. How much hydrogen would you need to store 1 terawatt of energy? Knowing that at that thermodynamic condition, 1 cubic meter of hydrogen stores about 132 kilowatt hour. So all you need to do here, is to divide 10 to power 12 by 132 kilowatt hours. Okay, the poll is over. I have plenty responses, and it's great to have everybody contributing. You actually would need item D, 7.6 million cubic meters of hydrogen for 1 terawatt hour. So it means that you need also a lot of space to store hydrogen. you need billion cubic meters of hydrogen to store the energy that you would like to have for Netherlands. Because you just, if as an engineer, I would roughly estimate it as we needed 8 billion Tesla car battery. Now here it's 132 in 50 bars. So about 100, 130, fine. It's about 8 billion cubic meters of hydrogen for 800 terawatt hour. Or for one would be 7.6 million cubic meters. There's a lot of a space needed to store hydrogen. So the challenge has been now converted from electricity-based batteries to hydrogen gas, compressed, and there you need to find a space to store it. If you find, you are just done. Because you have provided a way forward, a way that is feasible, not the way that, hey, you need 8 billion Tesla car batteries to store energy of the Netherlands. And you wouldn't have even minerals for that, let alone just the management and heat, and it's just unfeasible. So you have opened a new path here, but the path here would be complete if you can provide where do we store this much of gas. So how can we store massive amount of gas? We have different choices to store gas. We have surface-based facilities, tanks. They are very useful, but they scope very little amount of energy compared to what we are aiming for. For example, in Japan, you would find the largest liquid hydrogen storage tank, which is used for launching rockets to the space. And they store hydrogen there in extremely cool, cold condition. And then it will be used to basically, they fill them up before launch of the rocket or whatever activity they have, and then they simply are extremely costly, they are hard to maintain, and they are very, very secured, by the way, because it's extremely sensitive. And we have actually them in operation and for a long time. So they are not really new. So we know the technology of these type of surface-based storage. But when you look into the volume of the gas you need, the security, the land use, you can't really carpet the entire country with these tanks because you just simply want to live in this country and want to make trees and make it green. You can't use the surface for tanks and structures and buildings all the time. Even though at this scale, even they will be extremely costly, extremely sensitive, too cold, and it's a lot of work. And also would be then finally unfeasible. Where would you go to store massive amount of gas safely with no land, surface, not much surface land usage? You would go below the earth. In the subsurface, below the surface of the earth where we live, you can go down in the subsurface formations and utilize layers in the subsurface, whether you go about 1 kilometer, 500 meters, 2 kilometers below the surface, or 2, 3, 4, 5 kilometers below the surface. You can find reservoirs in which you can store massive, and I mean massive, amount of gas. In one of them, you can store 1,000 terawatt hour of energy. So in one of them, potentially you can store all you need for one country in the Netherlands. Okay, now in the rest, about 15 minutes or so of my talk, I am going to speak about the technicalities that are involved and sciences that are needed to advance in order to make this a feasible option for larger scale energy storage. And that is it. So the beginning of the talk, the first half of the talk was about the scope. How much energy do we consume? How do we store? Can we store it electricity based? What else we can? In other form, which is gas. What would be then the missing link here, which would be the space, where to go, subsurface formation. Now I'm going to talk a little bit more about subsurface storage of hydrogen and the sciences involved. And I hope you enjoy the entire talk. And I have received some comments and questions already about whether the slides can be shared. Of course, after the presentation, I'll send you the link. Organizers will actually share the link of the talk. You can download it publicly from the surf drive of TU Delft that we have. So I let Javier know about the link of the slide. Okay, now what is now? I'm going to now become a little bit now a bit more scientist in a way that I would like to go a little bit more to technical sciences, fluid mechanics, rock mechanics, and stuff like that to make you also enjoy about a bit of more science. Whether you go in the layers of the earth where we have rock salt, or we go even deeper where we have oil and gas reservoirs or aquifers, we can utilize all of these formations to allow us store hydrogen, whether in cavities, in salt caverns, in caves, or inside the pores, small, narrow microchannel pores of rocks. As you know, rocks, I usually have rocks on my desk, but not in my hand reach. Rocks have pore structures. They have empty void space inside them. 20% to 30% of them can be void if it's, let's say, sandstone. So whether you would create a cave by injecting fresh water and producing salty water to create a cave, you can have space here to store cyclically your hydrogen. Or you can go to depleted gas reservoirs or aquifers. There you have porous rocks. Inside the pores, you would store hydrogen. These are the places where we had, for example, gas stored, fossil gas. Now we have green gas. We can use the nature solution already and do the same thing as in nature happened. Gas was stored in fossil base. We want a green gas to be stored in larger scale. Let's go and find those reservoirs and store our hydrogen or green gas in those reservoirs, because gas, natural gas, gases were already stored there. Here the challenges are, you cyclically would store and produce your hydrogen. You would like to store your hydrogen fully inside your reservoir. Remember, hydrogen is the tiniest molecule on this planet. It can escape many places. It can escape almost every trap. It's so mobile and it's very tiny. So you need to make sure that it would stay in salt rock depositions where you have salt cavern is actually a good seal for it, but with porous as well, you need to make sure that it would stay and would not, for example, leak out. You need to also maintain its purity. When you store hydrogen in these batteries, which are the giant spaces under the surface, you need to make sure that hydrogen stays as pure as it was injected. So it wouldn't mix with the existing fluids or gases in the reservoir, whether cushion gas or existing gases, or it would not really get trapped. So, or it would not react. So it wouldn't have some activities there to actually react and change its purity. So mixing, change of purity if purity of hydrogen is changed, when you produce it, it is not as pure as you injected hydrogen. There you need to do filtering and do post-processing, which would also add to the costs, but still possible to purify. And obviously there is one other thing, is that you need to operate this system below the critical stress. You cannot push too much hydrogen at extremely high pressure too rapidly. You may just crash rocks. And on the layer, you may activate faults and they may slip. because it's just too much of pressure for them or too low pressure for them. So you will alter the stress field in the subsurface, and then you will cause damage. Yeah. So you need to make sure that you are operating in a safe zone, and you would actually make sure that the system stays safe. So these are main challenges that you would have in order to make things right in the cyclic manner. Do we have these places? Yes, we have. In the North Sea, this is where we live in Netherlands, there is going to be a hydrogen power plant to come to the grid in about 2030, so about 8-9 years from now. It's a massive project between many partners, which is aiming to produce 3 gigawatt power of wind for production of hydrogen, green hydrogen. And in the same vicinity area of that power plant, the blue dots show zechstein salt, or just total salt rock deposition, where you can actually go and mine and create those cavities, those salt caverns. So you're producing hydrogen where you actually can store it in salt depositions there. So we have the place there. You could go all the way to aquifers or depleted oil and gas reservoirs. These are the aquifers in the US which were identified for CO2 storage. You can use them for hydrogen storage if you want. The difference between salt caverns and aquifers is that first, salt caverns are cavities. Hydrogen would go into a cave. In porous rocks, hydrogen would go inside the microchannels of rocks with minerals, with compositions, fluids and rock properties there. And there you would have massive, a lot more space available for hydrogen in aquifers compared to salt caverns. And these are the different shapes of salt caverns that you have already existing in the world in different locations like Kiel in Germany and other places. And there are existing 4 caverns for hydrogen in the entire world, in the entire planet. There are 4 caverns. The first one is in Teesside in UK, which has been operational since 72. Not much data about them are available, and especially for hydrogen energy transition, you need to scale them up massively. You need a lot of them, a lot of them. Some hundreds of them need to be created in the North Sea if you want to store hydrogen storage in the right way. Okay, now we go to a little bit of porous reservoirs. They are in the offshore or onshore subsurface formations where you can store energy like this. And there are porous rocks. As I said, the hydrogen would flow inside the pore structure of this formation. And where do you think this reservoir in the subsurface is located? This picture that I'm showing is actually about 2.5 kilometers below TU Delft campus. So this is a reservoir, Sandstorm Reservoir, that is actually in Delft city. Yeah. So you could actually, this is what I'm trying to say, is that these subsurface formations exist and reservoirs exist anywhere. You need to just locate them. You need to appropriately manage them and see if you can and if you want to store energy in those subsurface formations. What are the scientific aspects related to it? I need about 10 minutes max to finish my talk, and that's it. There are many sciences involved in making subsurface hydrogen storage a successful program. You go to hydrodynamics, flow in porous media becomes very important. Geomechanics, mechanics of the solid skeleton that is the rock that hosts your hydrogen. Geochemistry, microbiology is very important. Thermodynamics of hydrogen, policymaking, licensing companies to operate, monitoring it, observing whether hydrogen will be safely there. Exergy analysis, how much CO2 we are going to save by that, techno-economics, and more importantly also, societal acceptance. Whether the society would allow you go and store it in Delft. If not, then you need to go to Rotterdam. If not, then you need to go to other. With the storage, you have the liberty to actually decide where you want to store. But societal acceptance is crucially important to be taken into account. And just a snapshot of what microbiology could do. There are bacterial activities in the subsurface as well, and they could enhance reactivities of hydrogen. This is a salt cavern where you have hydrogen at the top, some brine and some sump here. So you would store hydrogen in this tank. And the scale of the tank can be 500,000 or a few million cubic meters of hydrogen can be stored in one of these caves. Some million could be, or 500,000 easily. About the rocks, porous rocks, physics is at the microscale channels where hydrogen could flow. And there you have a variety of scales that would matter in order to allow you, excuse me, safely and efficiently store your hydrogen. Properties of the reservoirs are heterogeneous and they are very complex scientifically, so we are currently studying them significantly in depth and many other places as well. And data collection about them, seismic surveys, electromagnetic observation, and so many other forms also are very important to allow us understand how the reservoir really in the subsurface 2-3 kilometers below our surface actually looks like. And how do we develop a site to make it, for example, a storage for hydrogen or for storage of CO2 or a storage of any type? We start by understanding the constitutive laws in physics, thermodynamics, chemistry, understand our dynamic model, do modeling simulation, and then collect data and do optimization and resolve our uncertainty. We connect the link between this microscale physics to kilometer scale operation in geosciences. And for CO2, we have done the same path. For CO2, we have estimated how much CO2 will be stored by different physics from the pore scale, from microscale, all the way through heterogeneous, larger scale, kilometer scale of reservoirs. This is a cartoon which it shows when CO2 is injected into the system, how would it behave? You see, this is now being injected. Now it's going to be dissolved into the brine. And with hydrogen, we are doing the same in Delft. We recently have established and launched the project 2 years ago to understand how hydrogen behaves in the subsurface. So we have a laboratory, for example, a study to understand if, for example, this is a gas nitrogen in contact with brine and rock reservoir, to understand what would be the contact angle or physical properties here. We benchmark the process for nitrogen. Now we are releasing hydrogen from the tanks in pressures about 100 bars to see how it would behave through the time and this is exactly hydrogen. In 100 bars, it could be, and in different, after some time of minutes, the bubble of hydrogen is getting smaller. So we monitor it, we measure the property of it, and understand what hydrogen does in the subsurface when it's being trapped and stored in the subsurface. These are experiments which allow us then do modeling at the porous scale, at macro scale, to understand some functions, behaviors, and there allow us to do more larger scale simulation. How about rock mechanics? We test them in the lab, do cyclic mechanics because we are cyclically storing, producing hydrogen. We observe how the rocks behave in this apparatus. It's a huge apparatus. How is it behaving with a stress and a strain in cyclic loading to see whether only elastic or plastic deformations can happen? So how do we operate the subsurface in order to make it always safe? And these are the work that we do to get the formulas that you also study through your education of undergrad, grad, and PhD to understand how the nonlinear mechanics behave. How is a stress and a strain related to each other? In our models, we try to match the dots, which are experiments in those cyclic loading experiments, with our models to make sure that we correctly capture them. And so we put them in practice and understand how much of hydrogen we can store safely in the salt cavern or in the porous rocks. And these are all based on the experiments and models that are both combined. Last is about now with those coupled processes for pressure, heat, for enthalpy, temperature, we have a slow processes, fast processes, modeling, partial differential equations related to them. become very complicated, especially when you have in the subsurface very complex situations. We develop larger scale simulation platforms, mathematical formulations, computational sciences to understand how much of hydrogen we can store safely in the subsurface. To end my talk, subsurface reservoirs are giant batteries if energy is converted into the form of gas. Many sciences are needed to make it a successful project, from hydrodynamics to geomechanics, all the way to licensing, techno-economics, societal acceptance. And it's a diverse world. It will be more diverse. Also, energy will be diverse for this symposium, and energy storage is a diverse platform, and even hydrogen storage is a diverse sciences are involved in making it a successful project. Thanks a lot. I hope you got a good message from the talk today. We have a lot to do, and so we hope that all these talents, young students from everywhere who are connecting through this channel, get more energy, get more enthusiasm to enter the energy and solve this existing challenge of how to switch off our fossil-based 800 terawatt-hour to 30,000 terawatt-hour one day and successfully transit towards a green supply of energy. Thanks very much.
Thank you very much, Hadi, for your presentation. I think a lot of people become very inspired out of this. Is it possible to have 5 minutes to do some questions and answers from the audience?
Absolutely.
Hello?
Absolutely.
Perfect. So there's one person that I like. Sorry if I'm going to pronounce your name wrong, but it's Harsh Vardhan asks, thank you for the presentation, sir. I'm worried about the possible okay. I'm worried about the possible leaks that might occur. It could pose great security threat as well. Could you please throw some light on this aspect?
Excellent question. That's absolutely something very important, and we are really working on that. Let me just explain a little bit more technical. The matter of hydrogen being stored in the subsurface, as I said, is not purely new. Since 1972, there was a salt cavern for hydrogen storage. So we know how to do the storing. We don't know how to scale it up and make it a couple of hundred of caverns together. So in practice, we have actually a bit of knowledge, although these are really private knowledge and the companies do not share them. There is a risk of leakage of hydrogen, absolutely right, but we have mitigation procedures as well. The first thing you need to do is to properly choose your reservoir. When you are deciding where to store, you naturally avoid reservoirs which have natural leakage path, like faults within them, so that it could, or fractures that cross outside the reservoir. The other thing is that their cap rock, there is a very hard rock on top of many gas reservoirs. These rocks are really tight. And so if they are even, we have, let's say, brine in them or water, very interestingly, hydrogen dissolution into brine is very small. As if when you have a tight rock with also brine somewhere or water subsurface, it can really trap it. In salt caverns, since the salt structure and lattice is so tight, it's really sealing. The chance that hydrogen could leak would be mainly through the wells, close to wells if there are cracks created or so. So proper monitoring would save that, and proper site selection, and making sure that the reservoir has a cap rock perfectly sealing for the hydrogen. And I think all of them are scientifically possible. Yeah.
All right. I hope that answers the questions.
Yes.
We have another one from Nikun. This technology has the same problem as pump hydro, doesn't it? It's limited by geography and can be used everywhere, especially where it's needed, close to cities. So
that's another excellent question. In my view, it actually is much less limited compared to pumped hydro. In pumped hydro, you're absolutely right. You need higher mountains, lower mountains, or some natural elevation to pump it up upstairs or so. Here, you have a lot of hydrogen. You see whether you have rock depositions, you can utilize rock salts for salt caverns for our storage. You have aquifers, you utilize them. You have other reservoirs, you use them. Like in TU Delft, in 2 kilometers below the surface, we do not have salt cavern or salt rock, or we don't have gas reservoir. What we have is a sandstone reservoir 2 kilometers below the earth. And so we can potentially utilize that for hydrogen storage. So I see a lot more opportunities for this because variety of options are available, and you can always go down in the earth to reach some porous rock structures.
Perfect. All right, thank you. Another question from the chat box that I thought was interesting is about the using or the repurposing of spent oil fields for this practice. Is that feasible? Is that a possibility?
To store hydrogen in old oil fields or gas? Absolutely right. In fact, one of the main targets of larger scale porous rocks for storage of hydrogen is depleted gas reservoirs. So if you have depleted gas reservoir in the vicinity of the place where you want to store, you know that gas, methane, was already trapped naturally in that reservoir, and you know a lot about that reservoir because you produced it for so many decades, then you can use that knowledge to now store hydrogen there. And there are many companies today that are working on making depleted gas reservoirs for hydrogen storage purpose.
Perfect.
Absolutely right. Excellent questions.
Thank you very much. And we can do one more technical from Shanshank. Given we need to store hydrogen at high pressure, why does the storage unit has to be stationary? Injecting can be done at a low pressure, which is quite feasible, whereas its extraction can be dynamic, which can help us save energy in terms of both injection and extraction. Is this feasible?
Well, very, very interesting question. Thanks a lot for sharing your idea here. The reality is that when you're operating in reservoirs 2-3 kilometers below the surface, you actually cannot operate in lower pressure than a minimum pressure. You cannot make it extremely low pressure because the land above it, the layers above it could just collapse because you're making a lot of low pressure below this. If you imagine layer cake or layered system, you are depressurizing one of the layers significantly because you're operating in low pressures, then it may not be able to withstand the load above it. So we have a minimum pressure and a maximum pressure. You cannot exceed the pressure from a maximum limit because you may push then the land upward and then you see uplift. Yeah. So there is a range of safe operation, and there you're absolutely right. Within this safe range, you have a lot of creativity to do in order to store and to or inject and produce. You don't have to operate in one well, by the way. You can create many wells and store, produce, and sometimes you are having a line connected to injection and you don't want to change that. You just keep that as injector, and in some couple of meters or 100 meters from it, you make your production, for example. You might have 6, 10, 20 wells in one reservoir to appropriately manage how are you going to store, how are you going to produce. But this is true. If you could maintain constant injection, it means that you can rely on constant supply of energy in renewable sector. It's hard to do that today. So there are sunny seasons where you have a lot of solar energy. Maybe you will have a lot of hydrogen supply, but in low solar seasons, then you may not have that. Then it's hard to assume that you would have a static constant injection rate in your reservoir. But production side, absolutely right. When you have stored it a lot, now how to supply to the grid, it's all your choice. Whether you want to have it in a fast way, you would have it from many wells, like 5, 6 wells. There was a study in Germany, assuming 6 or 8 wells that would be used to actually produce hydrogen, depending on the scale you would like to supply. Now, one thing that I also did not mention is that it's not about minimum and maximum pressure, and between that you have all the flexibility to exploit, but also about the rate as well. If you quickly change the pressure of the subsurface, you may cause some dynamic effect to happen. And so you need to be very, very careful and understand your system before risking it too much with massively injecting or massively producing a lot of energy in a short time. You rather avoid doing that. And by the way, gas storage, natural gas storage, is taking place for many, many years already. We know how to store methane, natural gas, town gas, in the subsurface formations. Hydrogen, we don't have this much of experience at all. So scientifically, we need to really study how would this hydrogen behave, and this is very exciting. Many universities in the world are working on it. In India, also some colleagues are working. Australia, UK, here Netherlands, Germany, Austria, US. It's many, Switzerland and other places as well.
Perfect. Thank you very much, Hadi. There's many more questions, but due to time, we cannot answer all. But we're going to download them as a file. I'm going to share it on the server for the participants.
Thank you very much.
Thank you for doing this and for participating. This is a pleasure and an honor to have you here.
My pleasure. And
well, we're gonna take a 2 minutes break before the next speaker, and hope you all tune in for the next session as well. And
thanks very much. It was my true pleasure and honor to speak. Also, those who are interested, feel most welcome to get in touch. Send me an email if you wanted to. I'm going to send the link of the presentation to Javier as well.
Yes.
He can share it with everyone.
That's perfect.